And good morning. Welcome to the Firmware Security 101 Fundamentals webinar, sponsored by the UEFI Forum and the ICWG, the Industry Communications Working Group of that forum. And today, we have with us several experts in the field of firmware security, and I'd like to introduce them. I myself am Michael Crow, the chair of the UEFI Industry Communications Working Group, and I'm a systems engineer with Intel. With us today are Tim Lewis, who's the CTO of Inside Software. He's the former chair of the UEFI security sub-team and one of the original contributors to the UEFI Secure Boot strategy. He is a member of the Control System Cybersecurity Association, CS2AI, and oversees Inside secure development processes. Hello, Tim.
Good morning.
Also is Eric Johnson, a senior software engineer and the security coordinator at American Megatrends Incorporated. His experience includes secure software development for the firmware surveillance industry, U.S. government information assurance policies, and the payment card industry security standards, and now UEFI firmware security. Good morning, Eric.
Good morning, everybody.
Also, Dick Wilkins. He's here representing Phoenix Technology, as well as the UEFI Security Response Team, also called the USRT. Dick has been involved with platform firmware, including ACPI and EFI, for more than 20 years. As a member of the UEFI Board of Directors, he founded the UEFI Security Response Team 4 years ago. And good morning to you, Dick.
Good morning.
And finally, Vincent Zimmer is a senior principal engineer at Intel. He is the chair of the UEFI Network Sub-Team, chair of the UEFI Platform Initialization Working Groups, a security sub-team, and the UEFI Specification Working Groups security sub-team. He's also a member of the Trusted Computing Group and one of the most prolific speakers on firmware security. And good morning to you as well, Vincent.
Hey, good morning, everyone. Glad to be here.
And this is sponsored by the UEFI. So I'd like to start off, though, first with a question to the audience. What is your greatest area of concern with UEFI firmware security? And you can select any of the answers that are given: maintaining trust, updating firmware, responding to possible exploits, or understanding dependencies. Please pick one, and we'll be talking about these later on during the webinar. In the meantime, we'd like to talk a little bit about the UEFI Forum's philosophy. The UEFI Forum is a community that's based across the entire computing industry. We have representatives of just about anything that goes into or onto a computer in the UEFI Forum. And in the forum, there's a philosophy of collaboration and working together. And well, I'd like Tim Lewis maybe to speak a little bit on this part of the.
Sure. So one of the things that has always impressed me since the beginning of the UEFI Forum is the fact that people who are competitors in the marketplace sit across the table and work together to hammer out the specifications. So we may have different implementations, different strategies. We may fight over the same customers, whether it's in silicon, firmware, or somewhere else. But when it comes to security, we work well together and have worked together to advance the industry.
And that's one of the things that I can always keep seeing in this. I see people right now, we have members of different competing companies right now on this webinar as panelists working together for the message of firmware security. And talking about firmware, firmware is a point of attack. This is a recent development in security, as I understand it. Vincent, what brought this about?
Sure. So yeah, I think attacks against computer systems have been there from the beginning. If you see Multics in the 50s, but I think what's really changed with respect to firmware and security, as operating systems are getting more hardened, hypervisors, attackers have been moving down the stack. And I think having, a well-defined set of interfaces and consistency of platforms also helps them amortize the value of their attacks. And so I think the hardening of the stacks above and the more ubiquity of standards-based firmware has been driving a lot of activity into attacking the firmware, as evidenced by the Black Hats and other conferences that I'm sure folks on the list here have been seeing.
Okay. Yeah. Yeah. One of the things about these standards that I wanted to notice and mention is that because of these standards, we're working together with a standard that allows for a greater effect over the architectures. And in fact, I think, Eric, you had something to say on that in our pre-meeting. Could you expound on that a little bit?
Yeah, one of the great things about the UEFI forum is that it's made up of silicon vendors, operating system vendors, OEMs, ODMs, and of course the independent firmware vendors like AMI. Because of this, the specification is very flexible. You can run it across pretty much any type of silicon that's out there. And as an independent firmware vendor, that's important to a company like AMI because we provide firmware solutions that run on all these platforms that support the security standards that have been defined by the UEFI specification. And we're able to provide the same level of security across all of the platforms that we support, which wouldn't be possible without such a flexible and useful specification. And this specification also allows us to provide our customers with a product that they can differentiate, use to differentiate themselves between other ODMs, and at the same time provide a system that's easy for everyone to not only secure but to use, whether they're an OEM, a manufacturer, or an end user.
Oh, okay, that's great news. So with that, we're talking about firmware here. Which, as I said, we've talked a little bit about a firmware as a point of attack. Dick, because of your work with the USRT, you might be able to expound a little bit more on that and how it all ties together now. This cooperation, this specification, this flexibility into a solution space.
Sure. As Vincent said a moment ago, since the rest of the ecosystem, operating systems and applications, and network stacks, et cetera, are becoming more and more resilient to attack, it's moved into the firmware space. And that's a particularly valuable target for the bad guys, because if they can attack firmware, they can get control of the machine before the system even starts up, before the operating system loads and applications load, and they can control that environment entirely. Also, if they can get into that environment and reach into the persistent state of firmware, they can be there even if you reinstall your OS, wipe the machine, you still have the firmware there, and that allows them to completely attack anything that loads after that. So the purpose in particular of Secure Boot, as the slide here says, it starts from the moment you power on the hardware and creates starting from that root of trust, a chain of trust that goes through all of the firmware startup processes, hardware initializations, finding the system to load, loading the software, loading the OS, and potentially right out to the load of the application. You can maintain a chain of that trust through the entire process and keep that under control.
Okay, and that establishes that not only is the firmware protecting itself, but it's protecting the entire system for as long as the system wishes to be protected, it sounds like.
That's right. It's important that operating systems and bootloaders and those kinds of things continue that chain of trust. While that's outside the scope of what UEFI deals with, we provide that root of trust right from the hardware, right out through the load of the OS. But it's up to software beyond that to carry that on.
Okay. Well, let's swing back, I think, to the next slide where we talk a little bit about UEFI firmware capabilities and features. And I just let the panel discuss this a little bit, because you've all worked on the specification, you've all worked in establishing these capabilities. Let's just talk about these for a few moments. Thank you.
Sure.
Anybody can start.
Sure. So one of the key things about UEFI is UEFI relies on the fact that the flash device where the firmware is stored is secure, that it can't be tampered with. And that means, but at the same time, we realize that bugs happen, security issues happen, and that needs to be updated. So UEFI had to say, okay, how are we going to handle the case where something which is supposed to be tamper-proof, like the flash device where the firmware resides, how does it then be updated securely? And the mechanism is a standardized mechanism, which is being widely adopted, is the capsule update mechanism, where you package up your firmware update into a binary blob, you hand it back to the firmware, and typically the firmware on the next reset can handle doing the update. So that specification now can be agreed upon by OS vendors, the firmware vendors, the OEMs, about how are we going to do this process? How are we going to keep the integrity of the flash device, maintain the integrity of the flash device? So capsule update's a great piece.
One of the nice things about capsule update is that it provides a package that can be cryptographically signed, so that the firmware can actually verify that an authorized version of the software is about to be installed before it actually performs any write of the flash. And it can also do a version check to make sure that you can't roll back to an insecure version of the firmware to exploit a vulnerability that you already know about.
That's right.
Continuing on with Secure Boot, since I started talking about that already, I think one of the most important things to know about here we're trying to make it clear about the cooperative nature of this is a few years ago when we were coming up with the Secure Boot process and figuring out how to sign binary images to make sure that they haven't been tampered with. I was at a meeting where we sat in a big circle and we had all the OS vendors, including the Linux Foundation and several of the Linux distros, Windows, Apple, the silicon vendors, many of the OEMs, the independent firmware vendors who are on the call today, and were all represented. And we went around and discussed and hashed it out among ourselves with all those people present, and came up with a mechanism that would work to allow this secure chain of trust, the secure boot process, to work across all those pieces of hardware and software. It was a fascinating thing to see, with all these people who are normally cutthroat competitors after each other and their business everywhere, coming together to solve this problem of a secure system.
It's one of the great things about UEFI has recognized, and you can see it in the security story, is that firmware has many pieces, many people who are interested in it working. There are a lot of different people who contribute to making the firmware work. Different people provide pieces of the firmware, whether it's silicon vendors with reference code, whether it's open source, whether it's OEMs with specialized features, whether it's plug-in option ROMs, whether it's OS vendors. They all have to work together. And Secure Boot doesn't work unless these people all kind of work together, talk together, play nice together. If they decide to, you could write your own solution, but the problem is that doesn't really reflect the way that the ecosystem works, where many people have to come together for your firmware to finally make it on the platform.
That's a very interesting point. That's one of the ones that comes back around again, is this collaborative and cooperative situation, because really, from discussions we had setting up this webinar, it kept coming back that firmware is an element of security and the security plan of a system, but it's not the only element. It's not the catch-all and do-all of security, and at least that's my understanding on this. But it is a good foundational moment for security on a platform. Any thoughts on the panel around that question or that statement?
Yeah, I think that's a good point, Michael. And UEFI and the firmware doesn't purport to cover your entire security posture. Once you launch the OS does a great job, but as Dick said, making sure malware can't persist under the OS, or scenarios where you have physics problems, like you need to install the OS or your disk is encrypted, such as BitLocker or other full disk encryption. That's where technology like the user authentication in concert with Secure Boot come into play, where you can't do the user authentication into the OS because the OS image is encrypted on the disk. So before you unlock the disk, you want to prove that the right user is there. And so having a stylized infrastructure to do user authentication, these entities are typically called pre-boot authenticators or PBAs. To ensure the right PBA is there, you can pin it with UEFI Secure Boot. If you want a PBA from WinMagic, McAfee, Microsoft, the Linux community, the extensibility of Secure Boot to sign the various entities. Various authentication token vendors can plug in to the user authentication, whether it's smart cards, USB dongles. That's where you see the richness of UEFI security infrastructure come into play, and then scenarios where you have to do it in firmware because the OS isn't ready or you haven't installed the OS. The standards helps all these business entities sort of come together.
And I think it's important to say also that UEFI is the one boot solution that has all of these things built into the specification, into its basic design, and all these folks got together and worked this out so we could all work together and play nice. Where other folks say correctly that, oh, I have this other open source boot solution, and there's 3 or 4 of them that are quite popular out there, and I can plug in a secure boot piece, or I can plug in an authentication piece or an update piece. And yes, those things exist, but they're not part of the original design and specification or architecture. They're pieces that have been pulled from various open source plug-in facilities, and they may or may not work, and they may or may not work together in a concerted fashion. And I believe that's one of the big advantages of UEFI.
Yeah. And so that brings us, back again to that standards statement, where everybody's working from the same playbook. So interoperability between these standards, or with the standard, or within the standard, is a strength to UEFI as a solution, because everybody's working toward a meeting of the minds, so to speak. And that brings into a question then, what are some of the challenges with firmware security? I can understand that if you're not working on the standard space right there, a non-standard solution may be a good solution, excuse me, but it may represent trouble when you try to integrate it further down the line. What are some of the other challenges that we would consider?
One of the biggest challenges with firmware security is the fact that even if you can fix a problem in code, every single manufacturer has to actually take that code fix, compile it into their firmware image, and then deploy it to their users. It's a different firmware capsule for every single motherboard out there. So the quality assurance and everything that goes into actually putting these fixes together and providing them out to customers is very time consuming, and is definitely something that is different for firmware versus like an operating system where a single patch should be deployable to all users of that operating system.
And that's because the firmware is so intrinsic to the hardware of a system that it's almost a part of the hardware?
Yeah, exactly. The firmware itself has to know information about how to communicate with the hardware in order to do the platform initialization. So it has to have a very intimate knowledge of that specific platform in order to get everything set up and ready for the operating system to take over.
Oh, so that could present us a handful of challenges right there, as I can see it.
Firmware is also kind of a constrained environment. It doesn't have, there's a lot, as firmware is responsible for initializing the hardware in the first place, you don't have a lot of code space. You don't have, the hardware may not be ready, may not have access to a lot of the resources like a PKI infrastructure that maybe an operating system would, with being on the network. So as a result, it has to be secure with a set of constrained resources.
Mm. Okay, so that can present another set of challenges right there.
And you've got to convince your end users that they really need to update their firmware. I can't tell my grandma it's a great idea to go update your firmware, because my grandma is going to say, look at me, and tell me that I'd better go do it. But it's just not. It's hard to convince people to take something which they feel is working, and they don't necessarily realize the threat, or they don't even know how to do it. So we need to make it easier.
There's also, I've noticed, I've heard that there's also a great deal of fear about that, because you're changing something rather inherent to your system when you make a firmware update, and that generates a certain degree of doubt or concern, especially by users who are afraid of hurting their system. What's the thoughts around that and on that?
Now, well, we've had a history, honestly, in the past of platform firmware prior to UEFI, typically, where firmware was a bit fragile, and people, old timers that have been around for a while, tell stories about trying to update their firmware and bricking their machine, turning it into something that was useless and had to have their motherboard replaced or something. Those days are largely in the past, thank goodness. The standard UEFI and the OEMs and all are quite a bit better testing process than what we've had in the past. And so updating your firmware, be it UEFI or whatever, is less of a concern than it used to be.
Mm. Yeah. And that brings us to one of our next questions, is general questions, is how does each company account for security if they implement firmware? I take it, updates are part of that, but security in general with firmware.
Well, I would say for firmware vendors, this is a topic which has really come to the forefront in the last couple of years, which is how do we write software that is more intrinsically secure, not just in terms of security features and not necessarily just in configuring the hardware correctly, but also in writing code that is able to handle the exceptional conditions that malware often throws at you, whether it's throwing garbage data or strange data at you and trying to get the firmware to elevate your privilege or something like that. So teaching, a lot of it's been revolved around teaching firmware engineers how to write intrinsically secure code and what are the issues. And I think that's kind of an industry-wide concern.
One thing, if you look at the UEFI website, every year they do a plug fest, and you can see that Dick, for instance, has done presentations on firmware security for probably the last 2 or 3 years. Intel's done quite a few presentations as well. This is something that we're taking very seriously and spending a lot of time and effort to not only cooperate with each other, but to also help train the engineers that are out there taking this firmware and deploying it onto their product.
And to give credit where credit is due, Tim, in a recent PlugFest, did a presentation on the security development lifecycle and the process that all vendors should be using. And we did one on best practices in our development. So we're trying to spread this knowledge around to improve the security of all implementations.
Okay. So again, we get back into that collaboration and that strength of working together to form a solution. So when something goes wrong, because if we're all human, mistakes get made, code, somebody finds an exploit, something happens. How does a company respond, or how do the companies typically respond to these, or is it different, or what can people expect?
Well, it's a topic for a later slide of mine, but it is a complex infrastructure that provides firmware into the various platforms and computers that folks use. And everybody has their own approaches, but all of the independent firmware vendors that are represented here today, and I believe the silicon vendors, et cetera, and operating system folks, all have their own processes for receiving and processing any security issues or vulnerabilities reported to them. And they take this very seriously because these reflect any that are found that are actual real are reflect badly on all of us.
Mm.
And it's you receive the issue from one of several different places. USRT provides a great mechanism there, and then it's got to go out and work into finding and seeing if it's a real duplicating it, then finding the fix for it, then sending the fix out to the OEMs and ODMs out there who manufacture these systems, and then finally, hopefully providing it as an update within a reasonable amount of time. And of course, we have to validate that nothing goes wrong because of the update. So there's, everyone has a process for dealing with this. It usually just takes a while for it to filter out there to make sure that the security fix doesn't end up causing more damage than the solution. So, and we don't want to hand you a fix and then have to send you another fix the next day. That would be a big problem.
One of the important things there is to be sure to disclose this information responsibly. Take time to actually research the issue, make sure that it's fixed before posting it out on the internet, because otherwise you're just harming the community at large rather than actually helping to benefit the security of everyone's platforms.
That's right.
Mm. That makes sense. I've been advised by our producer that we are open for questions from the audience as well at this point. So if you have questions that you'd like to bring into the panel, please feel free to send them on in, and we'll try to answer them during this webinar, or if we have to, we'll take them offline and put the answers on the uefi.org website later. But so we come back around, to the benefits of the UEFI specification, because again, we have a standard. Companies are going to have to work independently because it's their products, but because there's a standard, everybody at least is working with the same mindset or understanding. What are the security benefits of the UEFI specification, beyond that collaborative aspect or that interoperable flexibility that we should be thinking about or talking about at this point?
One of the most important things is that the specifications are not defined by any specific silicon or operating system vendor. Everyone has an opportunity to participate in the discussion and come up with a solution that is effective for everyone and not just the specific company's needs. We want something that we can use on Linux, on Windows, on Mac OS, whatever, Android, without compromising the security on other platforms or making life difficult on other companies. So it's all about providing security solutions that are well defined, but flexible enough that you can implement with any OS or silicon.
Yeah, the fact of the flexibility is incredibly important. A lot of people don't realize. They look at the UEFI specification, download a PDF file, and go, "Oh my goodness, that's huge." Well, it turns out that the vast majority of that is entirely optional, and you can pick and choose the security features and other features that you need or want based on your platform. Your security needs may be completely different whether you're building a high-end server with thousands of users versus a kiosk that's a constrained environment. You may need different features, and the specification provides a number of them. You can pick or choose depending on what you need, and it doesn't require you to, in order to be somehow compliant, to use any particular set of these. You get to choose.
One of the other good pieces here is that the spec is also sort of forward-looking. It's always looking forward to say, okay, at some point, someone's going to get really good at some sort of cryptography, and we're going to need some other business needs going to come up down the road. The spec is very forward-looking in the sense it's extensible. That's part, actually, its middle name, Unified Extensible Firmware Interface, and the idea that even with security issues, we're looking forward and going, okay, what's the next thing down the road? What's the next sort of attack? What's the next thing where we can help computer manufacturers and end users guard their system? And so that's why we have, we are always talking with other groups, including like the Trusted Computing Group, and saying, okay, how do we make this kind of work together in a seamless way to handle the next, not just the threats that are there today, but the threats that are going to be there tomorrow.
So
brings
we're
up
not.
an
Please go
excellent
ahead.
point. The specification itself is still under, it's constantly being updated. So as new types of threats become known to the world, the specification can be corrected so that we can handle those threats while still continuing to support and mitigate other, older attacks that have already been discovered.
Yeah, we're 4 versions in now since the original Secure Boot. We've gone through 4 major revisions since 2.3.1, right, where Secure Boot has been a de facto part of the spec. So it's quite mature. And it has adapted already to new challenges in security. So it already is doing its job, and I think it will continue to do its job.
So basically, the old saying, if you make a better mousetrap, you get a smarter mouse. And you're prepared for those smarter mouses by building even better mousetraps later. Mice, yeah. And so we were just talking Secure Boot, and you've said that there have been some changes. This question sort of relates to that, of the dependencies of Secure Boot and how those changes have come about, and what the directions are. Would anybody like to take this question? The dependencies of Secure Boot.
I think that probably the biggest dependency that people are concerned about out there has been, at least what we observe in the press, those kinds of things, is the signing process and the certificate authority. One of the things that's you have to do in order to enable Secure Boot is store secure keys in firmware in a secure location so that payload can be checked as it's loaded and the system is started up. At the time, the UEFI Board of Directors looked into creating our own certificate authority, and it turned out to be prohibitively expensive to do. And so we looked around to other organizations who might be able to help us out. After some negotiation and discussion, Microsoft agreed to essentially for free to offer their certificate authority as a mechanism to enable Secure Boot. A lot of folks immediately said, "Oh, it's Microsoft evil," which is not true at all. But there are the folks out there that have concerns, and that's a fair concern. And we have reached out to the Linux Foundation to see if they would like to start out a certificate authority. They indicated that they looked into it and indicated the same problem that we did. It's prohibitively expensive. We're always, the UEFI Board of Directors is always looking for another certificate authority that we could use, in addition to the folks at Microsoft have been nice enough to provide for us, to sort of provide an alternative solution. But anyway, that's an area as a dependency of Secure Boot is on some secure certificate authority to provide signature keys, but we're completely open to others in the future should someone stand up and say, "I've got one," and I would be happy to help you out.
And if you want to sign your own OS image and you want to sign your own flash updates, that's okay. You can do that with UEFI, right? The certificate authority that Microsoft provides is a convenience to allow multiple players to interoperate easily. But if you don't like that, go sign your own stuff. That's fine. It's all there in the spec.
Okay. Yeah.
Right. You can definitely self-sign your own certificates, and if you're a company that's running dozens of data centers, building your own servers from custom hardware, that probably makes sense to run your own internal certificate authority anyways. So the specification doesn't tie you to anyone as far as a certificate authority, but by using the UEFI CA that Microsoft handles for us, it ensures compatibility across multiple hardware vendors. So if you're dealing with a specific graphics card provider, you know that their option ROM is going to be cryptographically signed in a way that your firmware will accept it.
So basically what we're saying here is we have a security certificate authority that's understood by everyone, so that you can work with other firmware components, add-on option ROMs, and things that we really haven't discussed very much. But if you really want to, you can step away from that and say, I am doing something that is very secure or very specific, and I'm going to do my own thing using some of these standards, but I'm going to take it one step further away from the standards for my own reasons. And I can do that without any significant issue associated with spec or compliance. Is that an honest statement or an accurate statement?
People do it all the time.
Okay, that's a very telling element of this, is that not only are we working with standards, but you can step away from them if you find them too constraining to your specific security plan or profile.
I wouldn't even consider that stepping away from the standard, though, because you're still following the same signing requirements. You're just acting as your own certificate authority instead of using one that is shared in common amongst multiple hardware developers.
Okay. Oh, thank you for the clarification. I just wanted to make sure I understood what was being said here. Okay, so I'm working within all the standards, and I've discovered that there is a problem. How do I report security issues to, or who do I report security issues to? I mean, I found a firmware issue, and it looks like, I look at it and I discover this could be across the standard or across a lot of platforms and not just the ones my company produces. What do I do? I mean, I know I got to fix it myself, but this is going to hurt a lot of people if it's not fixed across the board. So how does that get resolved?
But this sounds like you're playing right into the supply, the USRT slide. The important thing about firmware, as we've described earlier, is firmware is very tied to the hardware, and it's very custom for each particular platform. Each particular computer from the OEM perspective, we'll call them SKU. Basically, a particular version of their platform has its own version of firmware, and that comes from a very complex supply chain. Most of the implementations out there start with the open source called Tiano Core implementation of UEFI. That's been out there for a number of years. They start on that basis, and then it may be customized by and value added by an independent firmware vendor, which may pass that on to a board manufacturer, an ODM, who may customize it further, and then they may sell boards to an OEM that builds PCs, and they customize it further, and in some cases it even goes to a distributor, which may put a different name on the box and call it something else and may customize it further. So there may be 4, 5, 6 different places where the firmware is touched and manipulated. And what we found in the past, that it's very hard to figure out who's responsible for a particular issue or vulnerability. It could be anyone along that chain of that supply chain of firmware. And so the UEFI forum recognized this as an issue a while back, 4 or 5 years ago, and created the USRT, the security response team, to deal with that issue.
Okay. All right. So at that point, you know, there's the question of, you know, how does the industry help? This slide here, bringing the whole thing together. And again, it comes back to this cooperation and this collaboration.
Yeah, getting the UEFI forum involved in any issue or problem discovered allows you to take advantage of this cooperative organization that we've developed and have everybody working together on a solution.
Okay. Well, I know we've mentioned this a few times. We've talked about the UEFI Security Response Team, the USRT, which is part of this communication and handling of things. I know that you're the chair of this, Dick, so I'll let you start off on this and tell us a little bit about the USRT.
Yeah, I won't spend too much time. We've kind of touched on a lot of it already, but about 4.5, 5 years ago, we noted that a bunch of security researchers and others had been probing UEFI firmware for vulnerabilities, and they found a few, honestly. And the problem they had, as I just alluded to, is they didn't know who to report these to. There was no central point of contact, and honestly, some people in the supply chain just were not ready to receive security issues. They didn't know what to do with them. So we decided that there needed to be a central point of contact to provide a place for anyone who found some sort of vulnerability or believed they found a vulnerability, to someone to report that to, and who would take responsibility of figuring out who actually should work on this. So the USRT has done that. We have contact information at the URL at the bottom of the screen there, uefi.org/security. We provide an email location, and a phone number to contact if you've found an issue or think you have. Also, if you're concerned, about sending the technical details over open email, we have PGP key there so people can encrypt their messages. And then we receive all of these and acknowledge them all and evaluate them and route them to the right folks. We have a notify email alias out there to notify the entire membership of UEFI of security vulnerabilities that have been reported. Because what we found is if there's a vulnerability in OEM so-and-so's PC laptop model, the chances are that other people have that same vulnerability. It applies because depending on where it comes from, it could come from the open source basis code that nearly everyone uses, or it could be something specific to that OEM, but other OEMs may have made the same mistake. So we do a broadcast notification of any real vulnerabilities we find, and then we work with the member companies to respond appropriately to these. And we will also act as an intermediary between the reporter and the various companies involved in rolling out fixes should a real problem be found, in doing appropriate notification of vulnerabilities, making sure that that we responsibly tell the public about these things once they've been available to be fixed. And one other thing I'd just like to say in this, we've been doing this for over 4 years now, and we've processed a number of reports. some of them being real bugs and real security flaws. But I'm happy to report to the audience here that all the ones that we processed have all been honest implementation bugs. So far, we have yet to see a reported problem that bears on the specification itself. The design, the architecture of the security features we've been talking about here, we have not found any flaws in those. We have occasionally found a flaw in an implementation of them by a particular coder somewhere makes a mistake. That's okay. We'll find and fix those and get the fixes out to the public, and we'll help make sure that happen. USRT doesn't do it. The OEMs do it themselves, but we'll help facilitate that. And if anybody has any questions on the USRT and the process we use or anything like that, feel free to submit those, and we'll add those to the questions we'll take at the end.
Definitely. And speaking of questions, I do have the poll results in from the beginning of this webinar. Right now, this is what we've got. They're being displayed. The strongest point is responding to possible exploits, which plays well into our last discussion of the USRT. Maintaining trust is the second. Updating firmware is the third, and the fourth is understanding the dependencies of everything. Let's talk about these in relationship to the UEFI security specification elements. We've sort of touched on all of these, but if anybody would like to take one of them and go a little further, I think that would be an appropriate use of our time here.
Well, obviously everyone's afraid of exploits, right? So exploits often get names attached to them, whether it's a firmware vendor name or a OEM name, and so CEOs probably lose sleep at night because for fear that a security exploit might be found in a solution that maybe they don't lose sleep. I don't know, but it's certainly scary for me. And so I think that we all worry about that. And I think that's why we're, trying to do timely responses. How do we optimize the process by which not only we find exploits, but then we can deploy the solution out to the end user? I think that's really, that's one that sits on everyone's mind. How does that process work? How do we make it more optimal? How do we, the time from an exploit being reported to us to the time that I can that it's in the hands of a user? How do we reduce that?
Which is also including the update discussion, I believe. But just a good point.
That's right.
Any other thoughts by any of the other panelists? Okay, I have a question from the audience, and it's what is the benefit of this chain of trust that we've talked about before and its approach to security? It strikes this member of the audience that it's a rather complex solution, or isn't it too complex? This becomes a question. Would anybody like to field that question?
Sure. So, yeah, I think the benefits of the chain of trust are, start from, you really want to start from the highest integrity component in your system. And so it could either be the silicon. So for Intel, you have Intel Boot Guard, which is something in the hardware that'll validate the initial BIOS UEFI code, or AMD has their PSP verified boot. The ARM vendors have similar. So you want something that, typically the trust anchors or the keys can be set with fuses, very robust, that can validate that this is the firmware implementation from the manufacturer. And then once you've guaranteed from the hardware that this is the vendor authorized firmware, it in turn can validate that the richer features like UEFI secure boot haven't been tampered with by external parties, and then it can validate the operating system. And the reason the chain of trust is important is the firmware really can't tell whether, the difference between well-intended software and malware. So it really needs to guarantee that the machine, as designed by the manufacturer, as validated in concert with the OS, is in the state that it was intended by the vendor. And it is complex, so the keys to validate your firmware updates and validate the initial firmware are different than the verification keys used to validate your OS and option ROMs. But with that, complexity gives flexibility to the supply chain mentioned earlier. You can have elements from the hardware vendors, you can have code from independent BIOS vendors, you can curate from some open source, and then the party building the final product can then authorize, this is my well-known firmware. And when they service it in the field, make sure those services updates come from the vendor. And, it's a chain because the initialization and then the later firmware and then the binding to the OS vendors have different trust relationships. The updates are authorized by the manufacturer, whereas UEFI Secure Boot may be managed by the end user, maybe as mentioned earlier by AMI, Tim and Dick, that you want to put your own keys in there. An end user should be able to do that, whereas perhaps in a corporate IT, you don't want the end user changing the underlying firmware. So that's sort of why I think end customers want the chain of trust, get the brand value of how the machine was built, and have it serviced in the field through the life of the platform. And the chain of trust is really how you maintain that in the field. So I think the end users want it. I think IT wants it. There's some enthusiasts that want to change everything, and there are classes of hardware where you can unwrite protect your flash and bypass some of these protections, but those are typically, enthusiasts that have physical presence. But I think the broad market really wants to know that the machine they have is acting as prescribed by the manufacturer.
And specifically about the chain aspect of this, if you think about it, if we've described the process from bringing up a CPU to initializing hardware to finding boot devices to finding the boot image, the OS loader, the OS itself, etc. Each one of those is a piece to this process. And you could write as secure a piece as you want to, but if you don't hand control from one to the other, to the other, to the other in a chain where that trust is maintained from one step to the next, then someone could slip in a sort of pseudo man in the middle kind of thing and could squeeze in between those independently secure pieces malware of some sort that then affects everything downstream from that step. So the chain of trust is valid because it prevents anybody from inserting something into that chain. You can't break the chain.
Okay. And I have another question that's come in about secure boot. Okay, we've talked about this chain of trust. How does that look? What does that look like in an example environment, maybe the cloud or something, where the system is booting remotely on a network for provisioning, then goes on to different boot stages, gets its local OS, starts loading its own drivers. How does that relate to an environment that people understand, so they can sort of understand the connectivity there?
One of the key here is that in a cloud environment, you absolutely have to make sure that every single component is trusted, because you're dealing not only with your own operating system, but potentially the operating system of your clients and people that actually provide you a revenue stream. You have to secure their data, and the only way that you can do this is by preserving the chain from boot up all the way through to loading those operating systems or those virtual machines for the cloud. And so the way each cloud vendor does this may be different depending on the hypervisor they use. But for instance, if you use VMware solution, VMsphere or whatever they call it these days, they support secure boot. I know that the open source hypervisor also supports secure boot, and this allows you to preserve that chain even into the OS that you're booting inside of the hypervisor. You can also continue that chain through the secure boot process, and thereby guarantee that nobody's tampering with the individual virtual machines as they come online.
Any other thoughts by any other panelists? I have another really good question. Okay, let's presume that an attacker succeeds in corrupting the firmware image, and the UEFI secure boot detects this and prevents the system from booting because the firmware has been corrupted. It doesn't pass its certificate authority. Now, a person has a system that won't boot. What's the process to get things straightened out on this?
There's a couple of approaches that can be done, depending on the OEM and the supplier and the particular firmware implementation. Clearly, the person involved can use some sort of mechanism for reflashing their firmware from downloading and reflashing their firmware. It's sort of the old-fashioned way of loading a new firmware image off the internet that passes the capsule update process to ensure that it hasn't been corrupted and it's the valid one for this particular platform. Many OEMs and independent firmware vendors are providing mechanisms to have more than one image in flash at any particular time, and if one of them should be corrupted, it fails back or fails over to the secondary image, comes up and allows you to get booted and then repair the image that's stored in flash and get back to a good clean state. There are many ways that this can be done.
A lot of it depends on your on how sensitive your machine is too, right? So some people will. The double flash images is a one. NIST has a standard that people are trying to implement using this sort of double image. Some people say that we're going to put better protection on one part of the flash device so that it's really hard to corrupt this piece, and that part has a recovery mechanism built into it, a boot block sort of scenario. So depending on the market needs for a particular one, it says, okay, how serious am I worried about someone being able to get into this box, and what part do I need to protect in order to make sure that I maintain that root of trust and I maintain my ability to recover from it. So there's a lot of different answers to that question in the industry, based, where's the system going and what's it used for?
Yeah,
right.
One other thing that really wasn't part of the question as such, but many times the hackers, whatever you want to call them, are trying to insert malware into the boot process. And the nice thing about the secure boot process is if it sees something inserted into its step-by-step process and sees that part is not correctly signed, it will just skip over it and continue to do the right thing and run the code that is secure. So the system may well boot and just ignore the malware that was inserted into the boot process, and so it will have no negative effect, which is a great answer.
And of course, in a data center environment, you could use something like a baseband management controller that is able to reflash the firmware if it becomes corrupt. A lot of the enthusiast hardware has a separate flash components with a physical switch, so that if somebody's in there tweaking their settings and they create some configuration that's unstable, they can just pop the case open and flip a switch, and they're on a version of the firmware that is not corrupted by whatever settings changes. So there are many options that are available. It just really depends on the market segment and how the specific manufacturer wants to address that issue.
Okay. Well, I've noticed that we're almost out of time, and so our last slide is our thank you. I want to thank everyone for attending. I really want to thank the panelists. for coming here and sharing with everyone. I know we had more questions and we didn't get to everyone's question. We have captured those and we're going to see about getting some answers to those on the uefi.org website, which is listed here on the slide, in fact. So if you didn't get your question answered, come back to the uefi.org website in a few days and we may have the answer for you there in a written form. Once again, I hope everyone has a good day, and we've really enjoyed this. Thank you very much.
Thank you all.
Thanks.
Hey, thanks.